Yeah, draft physics video presentation. Pretty sure it's working. Anyway, I'll do some comments and then some more photon stuff. Blah blah blah. You might want to do a response videos, do response videos to, I guess, other science channels like Fermilab. Well, coincidentally, I did have a Fermilab video that I was going to get around to on gravitational lensing. But I don't think it makes any difference, frankly. Also, explaining different phenomena we see, that might attract more open-minded people to your channel. There's no way to attract people. It's kind of a YouTube thing. Popularity begets popularity. It's a viral thing. You have to get the virus, or you don't got it. You're just stuck. Anyway, have you actually read any of Ken's works? In the word is perturbation, not perturbation. Who cares? Perturbation. Smart guy. Again, do you really think that I'm trying to get the word right? I'm making fun of it on purpose, frankly. It's a silly word in the first place, even if the concept meant anything to me, which it doesn't, because it's silly. Um, you know, I still would mistreat it because it's just a terrible way to describe something. It's a, you know, it's one step away from, you know, it's just not a nice word. I wouldn't want to be called one. A perturbator. It doesn't sound good. So fuck you. Anyway, nice video. I always like it when you walk through other people's presenting their models. The last half of this video about the photons breaking by the slits and the bars being spots where the right frequency align was very cool. Well, it's not a great way to say something, but fine, very cool. Very right, maybe is the point. But you're the one who gets it. I mean, frankly, this was a moment in history, and you all missed it. But it's the moment where somebody got the right answer to wave particle duality and explained why it's just particles. And they're doing a little bit of a wavy thing in the sense that they're breaking and recombining, but it's not even a wavy thing. There is no interference. There's just constructive remaking a photon or leaving it broken. Those are your two choices. So, and it's understanding that's the real concept. So, yeah, it was a big moment in history, and you just didn't even notice. Is that the first time you've presented that idea? Yes, it just occurred to me this week, the right answer. Partly because I realized how big photons are. I mean, it's one thing to talk about its wavelength, and you say, okay, that's big, 700 nanometers. They say how that's small, but that's really kind of big. Okay, I mean, considering the size of things compared to an atom, that's huge. That's 2,000. 700 nanometers is 2,000 atoms. It's a lot of atoms. So photons are gigantic, in terms of their polarization. Yes, it's first time. I don't think I've heard that from you before. Well, you're correct. And it was a moment in history. Blah, 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 blah. Da, 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 da. Anyway, so I think I'll go to drawings from here. Yeah, let's do slit first. All right, so, this is just it's got to be the right answer, but it just makes so much sense. All right, so photons are little bits of energy, however you want to look at it, quanta, at a distance from each other. And that's their wavelength. They're all moving the same speed, and they're moving generally in the same direction to be a photon. And so they can be thought of as bullets, and they're just fired a little bit sloppy. So they're parallel in their flight, but their flight is not exactly perfectly lined up. And so, and that distance happens to be commensurate to the distance of the width of the slit. So you can sort of imagine that if these two photons went in to these slits, that part of these photons would be damaged by the process. It wouldn't be good for them. I think I probably have to change this size, or this will be too big. Okay, for the purpose of drawing. So these photons, this one and this one and this one, the little bits, will probably hit this obstruction, and all you'll be left with is these two. Now, the point being made is that when humans register light, they register it based on how many of these little bits hit, and they're approximating about like 6. They could be talking about actual photons. You need 6 actual whole streams, but I think they mean just the quanta. But the point is for even our instruments to read a photon, there has to be enough of the frequency for us to be able to detect a radio wave, for example. A certain length of continuous perturbations at a frequency have to take place, and if they don't take place at the right number, the length of it, the radio receiver can't do anything with it. It can't say, I saw a piece of radio wave. It has to be enough for it to generate the appropriate response in the instruments. And the instruments are basically sticking an electron out and saying, hit this electron with your photon. Hit these electrons. See, that's the other part. None of these instruments can work without using atoms as the receiver. They have to use a collection of atoms in a matrix, and very tightly locked together, so all of the atoms can collect the signal and then combine the signal. And that's how all these instruments work. So you need a certain amount of signal to get to them. They can't see one of these things. They have to see them in the right frequency, that is the right distance from each other, and the right number of them. If they don't get the right number, they don't see it. So if a photon only has 4 of these little things, we don't see it. Frog might see it, but we're not going to see it. All right, that's enough preliminary. So these 2 photons, you could just imagine these are just 2 random photons that are coming in all kinds of conditions like this, and there's a zillion of them. So even though they're taking up a lot of space, they're piled on top of each other. So in a sense, it looks like a wave. So if I was to put a whole bunch of these, all at this line, and then this line, and then this line, all lined up at the same distance, you could say, oh, it looks like a wave. Well, it's a wave of soldiers, or it's a wave of bullets. It's still bullets, okay. And this sort of brings up, a video that I saw that was really kind of dumb, explaining light. And so his vision of wave particle was to put waves inside the particles. Waves are the emergent thing. They're the things particles do. Particles can line up in waves. The particle isn't a wave. It's so obviously wrong in terms of not understanding which one's elemental and which one is emergent, which one is a consequence of the elements doing something. Soldiers can make waves of soldiers. You have to have the soldiers. Bullets can make waves of bullets. You have to have the bullets. Water makes waves of water, but no, you have to have the atoms. The atoms are pushing each other. They're really just rays of atoms moving in a direction. All the atoms are moving. They're moving in this direction. They're pushing into the guy here. This guy here pushes into the guy next to him. He pushes into the guy next to him. The wave is a byproduct of what the individuals are doing, not the other way around. And that's essentially true of all waves. There is no elemental wave. Okay, wrong diagram. All right, so all this crap comes in, and the idea is it's all the photons are getting broken by the process. So when they go through the slits, they're getting damaged. A lot of damage to them, and they need to hit something to be re-registered as a photon. So even if they hit a piece of dust, if I put a piece of dust in here, the truth is that some of these bits from this photon or one of the other million photons will, in fact, these 2 pieces will hit this piece of dust because it's the right distance away, and so they'll still have their right frequency, and they'll basically, the ones that lost parts, like this one's going to lose these parts here, so these parts will get lost, and what you're going to have left is this of this one and these 2 of this one, and that will make a photon if you can receive it somewhere. If you can get both of those things to land in some section of space, it will be received as a photon, even though it's made out of pieces from 2 different photons. And so if I put a piece of dust in, the same thing can happen. 2 bits can happen to be at the right alignment. Now the alignment's over here in the sense that you have to have them at the same phase. So that's the word they use to describe when everything's lined up correctly. So if I fill in the blanks with the two blue ones at the right phase, it turns it into a photon. If I put them in the wrong phase, that is the wrong timing order, this can't be received as a photon. It has just as many elements of energy as this, but the energy is in the wrong order. And without the right order, you're not going to push the electron correctly, and you're not going to create electricity in your detector. So you're not going to detect this as a photon. You're going to detect it as heat, as a lot of other things, but you're not going to detect it as a photon. And it's not going to go through the matter the way the photon would, because the energy is in the wrong order. And so you're hitting it. You can't tip something over if you hit it hard twice and then don't hit it for a while and then hit it hard twice. You have to keep hitting it while it's moving in the right direction. So that's the only part that gets the constructive and destructive interference, is when you're interfering with electrons. Electrons care which way they're going when you hit them, like a pendulum would care which way when you poke it. If you poke it when it's moving away from you, you'll add energy. You poke it when it's coming towards you, you'll take energy away. So in that case, it matters. But in this case, it doesn't matter because there's no interference directly. So all you're doing is saying basically there's a distance from here to here that is one wavelength. That is, the difference in length of this ray is exactly the same distance as the distance between these little bits. So they can fill in blanks as long as they started in a different order. So as long as they're the right pieces in the right order, this will recombine to be a photon, and you'll end up seeing something here. Now if they're the wrong order, then it's going to be like this, the wrong phase, and you're going to get nothing. And this is why the photon experiment doesn't create the on-off, gradual on-off that you're supposed to see. Is because it's really dependent on phase. And there's a point where you can mess this up a little bit, but you can't mess it up too much. Like this little bit could be 700 nanometers distance, wavelength. And this little bit probably could get away with being 650. And this one could be 705. And this one could be 692. So there's some variation that's within the tolerance of the instrument that's going to receive it. And it's going to say, okay, I still saw that as a photon. The frequency was a little dirty, but it was close enough to right to add energy to the pendulum. Even though I sort of hit it a little bit when it was coming up, it was only a little bit, so I still added the energy I needed to add to make it do the thing I wanted to do, which is tip over. So it still works. You could fire the bullets a little bit off, hitting a log, and you could tip the log over even though you didn't do it perfectly. You did it well enough to tip it over. So there's tolerances. And so what you're really seeing in the width of this bright spot is the tolerances. You're seeing how much those photons can be off in terms of their alignment. They can be a little bit off, a little bit off, a little bit off, but if they're over a certain line, nothing. And that's why it's an on-off pattern. All right, now the reason why the photons diverge, okay, that is spread, can just be because they're interfering with these two surfaces that have a bunch of atoms with electrons sticking out, and you're plowing through those electrons and scattering the light. So basically the light's just scattered. There's no interference in space, and all you're doing is constructively putting photons back together or not putting them back together. So they're either in phase and the pieces will go back together, out of phase. It doesn't matter if you have the right pieces. You're going to put together something that can't be seen by an instrument. So even though it's landing there, it doesn't matter because it can't be seen as a photon. And that's the simple truth. You can't receive it as a photon because it's too broken. So you fix them here, you don't fix them here. You fix them, you don't fix them. And that's the pattern. The pattern isn't constructive, destructive. It's put it back together, don't put it back together. Put it back together, don't put it back together. Alright, so now let's take on the interferometer. Same rules are going to apply, except it's a subtle difference. So the big green light means the light going out to the beam splitter, which is really just a half silvered glass. So it's a half mirror. It lets half the light through, half the light gets reflected. And realistically, how well can you perfect that? You're making a half silvered mirror, and you need the mirror to be almost perfect to be able to not create a difference, that's going to screw up your comparison at the end, your phase comparison. But again, you're allowed some fudging. Well, anyway, so the heavy green is what comes in, and I changed it yellow for the one that reflects this way, and then blue for the one that reflects this way. So the light goes up as green, all right, and it goes this way as green. So you see that it's splitting the light. Now what it's doing is it's taking that photon we talked about before, this stuff that is polarized. That is, polarization is an indication of its height, and its wavelength is the distance between the little bits. And so they're heading into this thing, and what's happening is three of them, so to speak, three of the bits will go this way, and three of the bits, let's say, are down here, and they hit the mirror, so they go up this way. And the ones that don't hit, that go through the hole in the mirror, they're the ones that are going to go this way. So three of them went this way, three of them went that way. Alright. Now if I put a piece of dust in here, you'll still see this as a photon, because there's a whole bunch of photons coming through. There's not just one. So now if I did it with one, you wouldn't be able to see the beam, blah blah blah. There's no point talking about that. But so I could scatter an actual photon, because there's a whole bunch of these pieces going up here. There's not just one little photon going up. There's a whole bunch of broken photons. A whole bunch of photons are getting broken by this process, where part of them is being reflected and part of them is being transmitted. And so it can be one piece of one photon, it can be six go this way, all kinds of different percentages. But there's a whole bunch of energy that, generally speaking, has the same frequency. That is, it was all released at the same general time from the source. So there's a whole bunch of photons going this way, okay, at this frequency, okay, so at this rate of being fired. But there's a whole bunch of them, but the individual photons, what we would see is some kind of this one, this one, this one, this one, array, a row of them, and all those rays are being broken into pieces, but they still have all of their quanta character. They're still at a frequency, they're still aligned to some respect. They're just missing pieces. They have gaps in them, and they're short, and lots of things like that. Well, anyway, so the pieces go in both directions. Each photon breaks up. Not each. There's probably some that actually all hit the mirror or all miss the mirror. Some of them actually get through a hole, and some of them hit the mirrored piece completely. But most of them, based on how tightly the mirror is silvered, that is, how tiny the dots of silver are, most of them have a polarization bigger than the dots, and therefore they're going to get broken in one way or another. So you're sending one broken beam this way and one broken beam this way. They reflect off a mirror, and again, you have to understand the mirror is not perfect. The photon, the little bits, one bit could go and hit the first atom it sees, it hits. The next little bit could go 17 atoms deep and then come back, and another bit could hit even more. So now every time you're going through the mirror, you're making a mess out of those frequencies again. You're starting to change 700 nanometers into 650, 690, 6 some other number, and recognizing that how many atoms you're going through. Let's say 20 atoms is still very small distance. That's like only 3 nanometers. You could have 20 atoms in, say, even 5 nanometers. So it's not a huge amount, right? 700 to 795. So you're not doing too much damage, 695. But you are doing damage. And the LIGO theory is that they do this 1,600 times. They go back and forth 1,600 times. Well, 800 times back and forth. There's 16 interactions with a mirrored surface. So you can understand after 1,600 times, and you're losing, 5 nanometers per interaction with the mirror, you could be losing an awful lot of accuracy. Your phase is getting broken just by the interactions going back and forth. But anyway, that's a separate subject, so let's just get back to this. So this reflects and this reflects. So these little bits go up, and if the mirrors are perfect, we could say there's a perfect reflection. There are no such mirrors, but anyway. So the stuff comes back. This one comes back as the blue line, and now it's going to do the same thing. The piece is going to get broken some more. Okay, so now it's broken, and now it may get broken some more, or it may make it through. So at any rate, one piece might go this way and two pieces come down this way. And the same thing is going to happen when this one comes through. Is it could lose two pieces this way, and it could only have one piece that comes down here. And you see this in the experiment, in the sense that the amount of light you put in is far less than the amount of light you get at the end. I mean, it's glaringly obvious that the pattern you get down here, how come that doesn't show up? I guess that's where the ad is. Yeah, the ad's in my way. Okay, so the pattern you get at this receiving end, the amount of light you get is really small compared to the strong laser you shot in. And the pattern's usually in the form of the ring pattern. But the only one they concentrate on in most interferometry is they just look at this center, and the center goes from on to off, on, off for every wavelength change theoretically you make. So as you change the phase of one of these by moving this mirror, you're basically changing whether they're in alignment or not. So now you're taking a stream that is going this way, and when you're putting the pieces back together, you're lining them back up again. And the point is as you change these distances at all, you end up changing how they line up. And you can sort of obviously see, if I change where they line up and I try to make a photon out of that, it's really got twice the frequency. It's not the same photon. And certainly if I don't line them up perfect, then it just becomes some weird frequency where it's too close together, and then too close together, and then too close together, and nothing's going to receive that because it's actually two frequencies, and it's just not going to, no detector is going to recognize something that's got multiple frequencies in it. Our detectors just can't do that. So anyway, these little bits now finally get down here, and that's obviously less to work with. You lost some of your energy, half your energy went the wrong way, and you've broken them twice, so you have a lot of broken pieces. But some of them will reconstruct back into visible photons, and those are the ones you're going to register. And the point is that you won't register them, any of them, if you change the phase. If you break the phase, you got nothing. Even though you have the pieces won't add up to anything. So you have to have the broken pieces first, and then you have to have the broken pieces in the right alignment. If they're in the wrong alignment, it doesn't matter. You can't put them back together. You can put them back together, not necessarily will. I mean, even if they're in alignment, you might not have the right pieces in the right places to put any photons back together. But the idea would be is when they are lined up, then you can put the pieces back together. It'll work. But you're out of luck if they're out of phase. And that's basically how the thing works. Nothing's interfering. So again, you're just breaking photons through using an aperture of some kind, a small little space, something that'll break the photons. It'll tell half the photon it can't do what it's doing. It'll reflect it one way, and the other half it does something else. It's something that breaks the photon, and the photon's big. Again, it's much bigger than atoms. 2,000 atoms is the size of a photon's profile when it hits a surface. So it's really easy to make a surface that'll break the photon. And then all you're really going to see is you can change where they go back together or where they don't. And you can change it by changing the phase, because that'll either say they can be put back together or they can't be put together. And then you have to just rely on the fact that you've got enough of the energy still intact for the material to collect it and say, even though these are little broken pieces, they still have the frequency built into them, and I can make photons out of that. I can see that as being on, even though the on came from 15 different photons. Each one of those ons was from a different photon. It doesn't matter because I'm receiving all of the impacts. And all I care about is that there's a pattern of impact. So as long as the pattern of impact is the same, it'll say that was a photon, even though it's made out of a bunch of different photons, so to speak. Alright, so anyway, so wave-particle duality resolved. Finished. Done. This is how it actually happens. This is the right answer. It's just so obvious. So, yay for my side. We did it first. And such. Nothing else to say. It works. And it works too good not to be the right answer. It answers all the questions of how this thing works. So that's probably enough. Right? All I can do is, say, look, it works, and it has all the elements you still need. The particle part is still here. The wave part is still a little bit here, but not really, because the wave part was crap anyway. But the particle and whatever part, the part that just seemed more complicated than particles, I've explained why it's more complicated than just particles. It's because of this idea that photons are just so much bigger than you're really thinking they are. And that solves it. So anyway, that solved it for me. Yeah, that was the fact that was missing, was the realization that photons, the pattern of a photon covers a huge amount of space. The photon, the little bits, the quanta are tiny. Tiny, tiny, tiny. I mean, many millions of times smaller than an electron. Who knows? Tiny. But the space they cover is huge. And there can be a ton of them in that space. Okay. So, I think I've done it. I've done all I need to do. So, I'll call it a video. I mean, I'm not going to change the subject to the gravitational lensing thing. I'll save that for another day. So, until the next time. And such. I mean, really, it's a historic moment. I'm saying, this is like, Galileo's telescope or something. It's it's one of those moments you'd say, oh, I wish I was there. Well, you were here, but you didn't even know you were here. Yeah. So, anyway, till the next time. Such. I think that's it.